All right, let's get started. So first, by a show of hands, who in here identifies more with industry and who identifies more with academia? So industry. All right. Oh, wow. Academia. All right. Well, so it's about maybe 5-1 for industry for the people on Zoom. But that's fine. So I myself, I have been working in autonomy in academia for about 5 years. I've recently started sort of position at Apple, and I'm a sort of hobby 1 day a week professor now. But all of this is going to be on work that I do at UT Austin, and sort of it reflects the perspective of UT Austin. It has nothing to do with Apple. All right, so let's talk about why you should work on autonomy in academia. And so this talk has been prompted by sort of a lot of questions I've gotten over the years on why I work in autonomy. And it's always followed up by sort of a follow-up question or a follow-up statement. And this is either autonomy is almost solved. Well, and then you have to switch again. You're out of a job. Or, well, you don't even own a vehicle. Why would you work in autonomy? Or there's this huge imbalance between resources between academia and industry. And I'm going to address all of these, and then I'm going to tell you a little bit on why it's actually awesome to work on autonomy in academia. All right, so now to the statement, autonomy is almost solved. Let's look at sort of a short history lesson. So when do you think was the first driverless vehicle? When was the first driverless vehicle on US roads? You think it was like 10 years ago, 20 years ago, 40 years ago, 50 years ago? It was almost 100 years ago. All right, so the first driverless vehicle on a US road was sort of developed 100 years ago. It was radio controlled by a vehicle that was driving right behind it. And it prompted newspaper headlines that said something like, well, the mastermind of this vehicle, and there's like, it was called the Phantom Auto and all sorts of things. So people already thought they had intelligent vehicles almost 100 years ago. Then back in the 50s, there was sort of the next development of this sort of hype cycle, which was the Firebird 2. The General Motors had this prototype car that was supposed to follow sort of a wire that was built into the freeway to sort of do automated steering. And that was right about a year before we started having cruise control. And so together with these two technologies, they were thinking they could actually get to driverless vehicles. And here it already says like the electric brain of the car and all sorts of words like this. All right. Well, again, this was actually never built. This never drove autonomously compared to the radio controlled car. The first vehicles that drove somewhat autonomously were actually sort of came out of Germany and out of CMU. CMU was Elvin. This was a vehicle that used a deep neural network, or not deep, a non-deep neural network to drive, and it used sort of a very low resolution input video stream and directly translated it into steering commands. Now, Elvin didn't do accelerations and braking, so the solutions out of Germany did, and there they had sort of, back then they had very slow computers. And so what they did is they had a very clever approach to sort of zoom into different parts of the image and do vision to detect the lanes, and then fit curves to do sort of trajectory, to predict the trajectory at which a vehicle should follow. They also had some basic obstacle detection and had some emergency braking built into it. Now, throughout the 90s, the funding for both projects ran out, and we still didn't get self-driving vehicles. Now, the current generation of self-driving cars had their roots in the DARPA Grand Challenge. And it's really characterized by two things. A, really nice sensors, and a lot of them, and enough computation on board to do interesting things. And if you look at the self-driving cars that are on the road today, they're still fairly similar. They have lots of nice sensors, and they have a lot of computation inside the vehicle. And so if you look at sort of the trend of autonomy, you can see that there's all of these sort of waves of, we get a cool new technology, such as radios, such as sort of basic electronic circuitry, or enough compute or enough, just barely enough computation on a mobile computer. And every time we get this, we sort of think, okay, we're going to solve autonomy, right? And so I would say there are about 4 cycles right now. We're at the end of the 4th, but we're at the beginning of the really exciting 5th one. which is we have lots of data, we have great deep networks to do interesting things with these vehicles. And so we're sort of in between the end of the just enough computation to do something interesting and good sensors to we have massive data for everything we want. And so I don't think we're going to solve autonomy anytime soon. Now, to the second statement where, well, once autonomy is solved or we have a first proof of concept, I'm going to be out of a job. I also don't think that's true. Just because we started having basic airplanes didn't mean we stopped making them better. We actually have entire departments that sort of improve our airplanes. Now, there's also in autonomy, there's a much better example. We actually have autonomous vehicles, just not on this planet. We have autonomous vehicles on a different planet. And just because we had the first success in this, it doesn't mean we didn't improve and make these vehicles better. All right. So I don't think the notion that is true that we'll sort of all of a sudden be out of a job just because we have the first autonomous vehicle. Now, the second sort of criticism I get, and I get this a lot from roboticists, the second criticism I got is like, well, you don't own a vehicle. Why would you want to do research on something that you can never really test in the real world? And it's true, I don't own an autonomous vehicle, and I cannot test my policies on an autonomous vehicle. Now, the statement or the point I want to make here is that actually neither do real, like the big self-driving car companies. Well, they have vehicles. I mean, of course they do, but they don't have the vehicles to test that their policies work really, really well, at least not for every single policy. And so what working well means essentially is doing better than humans. And so human drivers have about one fatality over about 1 million miles traveled. Now, it's a little bit less than one in cities in the United States, and it's a little bit over one in rural areas in the United States. And so if you think of, well, now you have a policy and you want to show that you're doing better than humans, well, if you want to do this, if you want to show this with a decent confidence interval, you will need about 600 million miles of driving just to statistically show that by sort of driving your vehicle, you do better than humans. Now, let's say we drive at about 60 miles per hour, which is really fast. It will still be about 10 million hours. Now, this is roughly the time, this is like 1100 years, this is roughly the time from when the Vikings invaded England or raided the coast of England to now. So if you had a graduate student, recruited him in the Viking times and hadn't continuously drive till now, then you could on a vehicle test that your policy is good. All right. Now, obviously, you could say, okay, industry can scale this up, but it's still going to cost a lot of money. So if you pay all of these drivers minimum wage, it's still going to cost about $100 million to test statistically that what your policy does is better than humans in terms of fatalities. And I mean, I have no doubt that industry will eventually do this, but they're not going to do this for every single policy. All right. So, oops. And it's also not really how we evaluate things in computer vision. It's not like if you have your favorite deep network that does recognition, you're not going to go around with a camera and take pictures and show that it works. Well, really good students will, but they will also do other things. And so this is sort of the vision from computer vision evaluation from the 80s, and it really didn't work. What we do nowadays is we use big data sets and we make statistical arguments on big data sets. Be it ImageNet or Microsoft Cocoa or whatever other data set we have. And so I don't think it's a problem that we don't have test vehicles in driving as long as we have good data and as long as we can train and test off the road on that data. And there's really sort of three different sort of scales of testing here. The first one is sort of open loop testing, where you just let the vehicle that collected the data drive, and you just see, well, how well would you do if you made predictions on that original driving trajectory without changing the driving trajectory. Then there is a little bit of closed loop testing, which is, well, what if you let the vehicle drive itself and sort of take steps? And this is also sometimes called sort of log-based testing. But what you do here is you sort of record the environment and you keep all the actions of all the other agents fixed. And now you're sort of trying to sort of adjust your own trajectories to do better in this fixed pre-recorded world. And then finally, there's full-fledged simulation. There's multiple variants. You can learn simulation. You can use Carla if you'd want. There's many different ways. And I think that should be the way we evaluate our policies, because that's more scalable. And we can get to sort of millions of hours of evaluation in simulation without spending a lot of money. All right. Now, the final criticism I get is, well, you don't really have enough resources to compete with industry. So if I'm in academia, I have maybe my cluster of 8 GPUs per student, and I'm supposed to compete with big industry labs that have sort of gigantic racks of GPUs. And yes, this is absolutely true. This is pretty hard. And we also completely rely on data that we get from industry to do interesting experiments. And if industry would ever stop sharing this, I think this entire field would implode, but luckily they haven't. All right. Now, it's also not true. I think academia has one resource that industry definitely does not have, and that's the graduate student. And yes, it might be a bit of a joke here, but there's actually there's a very interesting sort of different role that a graduate student plays versus an industry researcher. So if you're a graduate student, you're mainly motivated by solving a problem, by sort of making progress on an idea. If you do this in industry and you go to your product team, it's like, hey, I have this great idea. And like, look, I had this small experiment, it sort of works. Maybe you can do this once, twice, but at some point they will get really annoyed at you and they will probably tell you, well, come back when you have real solutions to real big problems. And so this different sort of scope is really what I think what academia has that industry doesn't. All right. So in my view, all of these excuses I got over the years are sort of lame, and I'll just dismiss them for now. But I want to talk about is why you should actually work on autonomy in this day and age. And for starters, it's because it's a very challenging problem. It's unsolved, and you can still make a big impact. And you can make a big positive impact. A lot of vision problems have gotten a little bit of a bad rap over the years because there have been sort of bad applications of them. For driving, this is less the case. You can only make the vehicle safer if you trust that whatever company deploys it will do rigorous testing. And we're also in a very exciting transition from the driving that just heavily relied on sensors and simple vision or simple sort of planning to something that's a lot more learned from data. And also, I mean, always every time we sort of have a new method come in, it seems like, yes, this time we'll solve the problem. And this is clearly one of these times where we feel like, okay, this is solvable. It's hard, but it seems still solvable. All right. So let me talk a little bit about this transition and how sort of it impacts the research we do at UT. And so from sort of the DARPA challenge age, people started to heavily rely on Lidar perception. And Lidar sensors are great. They give you very accurate depth measurements in the scene. And you can do simple things like sort of ground plane subtraction. You already have very good object detection. And I can do slightly better if you use deep networks to do the entire detection sort of end to end. We had some work at CVPR last year that did this, but I think there's still something you can do better. And if you look at sort of the performance of our method that we had last year versus sort of distance to the vehicle, you start to see the performance drops rapidly if you go further and further away from the vehicle. If you're at a sort of a range from 30 to 50 meters, you have about a 40% mean average, a 40-point mean average precision, which means for almost half the vehicles or half the objects, you're not going to see them. All right. And this is an issue because sort of 50 meters on a freeway, that's less than 2 seconds. And I would argue the reason for this is one of the main reasons for this is that Lidar is actually quite sparse. So what I'm showing you here in the image is I'm going to show you a color image, and then on top I visualize the Lidar measurements that we get from that same view. And if you zoom in, you can see Lidar is extremely sparse, especially for objects that are further away. Now, one might think, okay, well, why don't we just increase the resolution of our Lidar sensors? Well, it turns out that's actually quite expensive. There's some fundamental physics behind it that make scaling these LiDAR sensors, at least for now, pretty hard. Now, on the other hand, color cameras, they are already at a sort of 10x, 100x scale and are much cheaper than our LiDAR sensors. The issue is really that they don't give you depth information. And so one problem that we're looking at in my lab is sort of, well, can we do a lot of the same work as LiDAR sensors, but doing it just from multiple color cameras? And sort of there's great competitions, new scenes, Waymo has sort of fun competitions. And over the past year, there's really been a sort of a shift in approaches to this. Used to be about a year ago, maybe 2 years ago, you had to know geometry. You had to know sort of multi-view geometry to do this task. Nowadays, you don't. And so the big shift has been really that we went from sort of geometric approaches to just learning geometry. And the way you can learn geometry is if you know the camera location and you know sort of the ray each pixel goes through, you can construct an embedding of just a single ray. You can also construct embeddings for points in the scene, and then you can learn a transformer to learn the geometric reasoning between scene and images. And so this is what we do in a paper that will be presented on Thursday, where we really sort of just build up these positional embeddings and then just have the transformer learn all the geometric reasoning. So no more headaches with sort of camera intrinsics, extrinsics. It's just all in one transformer. You hit the training button and you will learn geometry. Almost. All right. Now, there's also lots of other interesting open problems if you talk about perception. There's obviously the long tails, like there's, at least on US roads, there's lots of weird things you will see on US roads every day. There is sort of the issue that tracking is actually, if you want to do it very, very well, it's quite hard. And it has to do with the fact that you can have occlusions where your sensors don't give you any information for a certain amount of time. And then you would have to sort of connect these tracks, or at least connect the observations through time. And then finally, one problem that I haven't seen very much, but I'm super excited about, is trying to model things that you actually don't see. How do you model sort of vehicles that you wouldn't have, that you wouldn't see, or how do you model the distribution over potentially unseen vehicles or pedestrians or other objects on the road? And so there's really a long list of interesting problems that we have no sort of good and convincing answers for, maybe also no good standardized benchmarks for yet. Now, to me, the more exciting problem, though, is not the perception. It's not the first part of a driving stack. It's sort of the later parts of a driving stack. And that's where data really comes in. And so if you look at the way classical planning methods sort of work that were sort of developed or used in the DARPA challenges, the way they work is you start to enumerate sort of where potential traffic participants might go. So you might say, okay, this vehicle in front of me might turn left, it might go, this other vehicle might turn right, the vehicle in front of me might go straight, and so on. So you start to enumerate all possible futures. And then you're going to enumerate where you might want to go. And now for each combination of sort of a future prediction for other vehicles and for the plan that you would want to execute, you're now going to compute a score for how good this is. All right. So you're going to say, okay, well, colliding, no good. All right. But maybe if you follow a smooth trajectory that obeys all the traffic rules, that's good. All right. Then you're going to use the score to rank them, and then you're going to settle on one trajectory and you're going to execute it. Now, the main issue with this approach is it's actually really, really hard to score trajectories, because you need to know a lot about the world. You need to know where everything is moving. You need to know all the rules. And it's like, you can think of, essentially, it's sort of encoding all the traffic rules into the world, and maybe even more, sort of all the customs and everything else into sort of just one gigantic set of rules. And I do not think this will scale very well, and it will also not transfer very well to new areas. And so there's a different alternative, and Sergey in the previous talk already sort of stole a lot of the mojo of this, which is you could just learn all of this, okay? And it's a very simple learning problem. So you have some observations, and this observation can be a sequence of observations. and you want to produce a sequence of actions or a single action. And all you actually have to learn is a policy that maps observations to actions. So in theory, this is very, very simple. The biggest question is really, how do you supervise this? You could just do imitation learning, which is, I'm just going to collect this gigantic data set of observations and actions, and now I'm just going to use my favorite training algorithm, my favorite network, and my favorite loss function, and just hit the optimize button. And this somewhat works. It's actually what sort of the first neural network-based policy did. They used 5 minutes of training data to train their deep network, and it was able to drive at about 2 miles per hour. All right. Now, if you put this in a modern vehicle, it would not work very well. And Sergey already alluded to this. It's simply just because if you do vanilla imitation learning, what will happen is that you have a slight drift in your predicted actions, and that will accumulate and bad things will happen. And so the pragmatic solution to this is to just add a little bit of noise during training. And so that way you're going to learn to recover from mistakes that you might make. There's also a different approach that we had a few years ago, where you could just train a policy on very clean data on which this drift is very small, and then distill it down to sort of a bit noisier data. But the other issue with imitation learning is that all the data we actually have is, I mean, at least the one I looked at, is pretty boring. So it's sort of people driving this very expensive vehicle and sort of carrying sort of the pride of the company with them, because if they're going to crash into the tree, everybody's going to take a picture and put it on Twitter, right? So they really, really don't want to take risks. They don't want to take sort of risky behaviors. They don't want to sort of try to explore a little bit outside of their sort of safe comfort zone. Now, if you want to see risky behaviors, you can just go on Reddit. And I mean, there's clearly lots of bad driving behaviors. The main issue there is, though, that it's very hard to get the sensor data or the annotations for this, okay? So yes, you can get sort of bad driving behavior, but it's not in the form that we needed, all right? So one thing that we were looking at is, well, maybe the ego vehicle itself does sort of not take a lot of risks, but maybe there is another vehicle around us that we can learn from to sort of learn this more risky or more interactive behavior. And this is a paper that we'll have on Friday here, where we're just trying to learn an imitation learning policy from all vehicles that we observe. Now, this still doesn't quite get us to sort of full exploration, because we do not explore what else we could have done if we were driving differently in the current vehicle. And so for that, you really need to use some sort of reinforcement learning. Now, vanilla reinforcement learning is probably not going to work because you don't want to wreck your car. But we have sort of a variant of reinforcement learning where we're taking the state space of reinforcement learning, and we're sort of pulling apart the state of the ego vehicle from the state of the environment. And now what we're saying is that the ego vehicle can react to the environment however we want, but the environment cannot react to the ego vehicle. And so we call this the world on rails assumption. Now, what this world on rails assumption allows us to do is it allows us to take sort of classical reinforcement learning algorithms and actually evaluate them in a tabular form on offline recorded data. And so this is sort of a variant of offline reinforcement learning, but it's sort of it's a very efficient way to sort of build in a reinforcement learning objective into data that you collected just for imitation or sort of in an offline data set. All right, now what I really sort of want to encourage you to think about is, well, think about sort of how can we do planning and control? How can we do this later part of the driving stack using sort of the current fancy learning technologies? And this is, in my view, one of the biggest unsolved problems. We don't have very good existing solutions. We don't even have extremely good data sets or simulators or sort of infrastructure for it. And there's lots of creative potential for new solutions. All right. And so with that, I don't think there's many valid excuses to not do research on driving in academia. And it's super fun to do the research in academia, probably more fun so than in industry, because in academia, I get to talk to all sorts of industry people and they will actually tell me what they're doing. If I do this in industry, this might not be the case. Yeah, and so with that, I'm happy to take questions.
Hey, Philip, great talk. I particularly enjoyed the analogy to we don't all carry our own cameras. But one of the reasons why computer vision people are able to do that is because there's a sense of community trust that you report a result. It's on a data set, but we trust that it will run on a camera or deployed in a system. And it seems like that trust doesn't seem to exist in the other space. And the fact that you're here giving this talk suggests that you are aware that that trust doesn't exist. And that seems like a social political problem, not a technical problem, or more so. So thoughts, like how do we solve that?
I agree. I don't think it's actually a social problem as much as we don't have evidence to show that sort of the more offline evaluation works. And I think that the right way to approach this is for companies, for industry, if you can show that the ranking between what we do in simulation is stable and comparative to the ranking that we would get on meaningful metrics in the real world, I think that's sort of a first step to maybe to solve this in a technical way. To solve the sort of the social aspects of this, I honestly have no idea.
Can I ask a quick follow-up?
Yeah.
So that burden, you seem to be placing it on industry because it, like, academia doesn't have access to those systems. But do you think there's enough buy-in to actually have that happen?
You'd have to ask them. Yeah, I don't know. I honestly, I wish we would get there. I'm not sure if we will.
All right, thanks.
Yeah, so very nice talk. I have a little bit specific question, like for the cross view attention transformer one. Yeah, so for that one, like how do you think like the calibration of the camera will affect the result? Like when you train the network, you use one set of camera settings, and what if like in the testing scenario, maybe somebody moved the camera a little bit, it moves. So how does that affect the output of the result?
Yeah. So I think it does change. So right now we don't assume it's fixed between training and testing, but we assume we need to know what the intrinsics, extrinsics are for testing. And I think recalibrating the cameras on the fly would definitely be a great additional benefit, or even optimizing over the calibration. We don't do this right now. Now the transformer itself has the ability to also ignore part of geometric reasoning and use look at appearance. And that's what it does sometimes if we sort of probe in what it looks at. It doesn't just fully rely on geometry, it also relies a little bit on appearance. And that might be able to correct for some of the mistakes.
Cool, thanks.
Okay, thank you. That was a fun presentation. How do you think this current hype cycle is going to unfold?
Oh, okay. Oh, there's more. Oh, that's a good question. Well, I think it all depends on industry. They either run out of money before we have driving, or we'll have very good driver's assist. I think that's the two outcomes that we'll have. Are we going to go self-driving all the way in the next 5 to 10 years? I hope not. I mean, that would be boring. So yeah, I think the end is either we'll have a very good driver's assist, or sort of negative end is maybe to run out of money and sort of everything crashes.
That is a gloomy way to end this presentation. But let's thank Philipp again for this wonderful presentation.